Hello, welcome to Akamath Musings channel. This is a continuation of a series of videos called Playing with Fractions. We already went beyond fractions and now I want to talk about irrational numbers, in particular algebraic irrational numbers. Today's topic is playing with irrationals, or where is dual multiplication operation. So we considered dual addition, but where is dual multiplication? Why we didn't see it yet? So this will be a topic, and I will show the connection between this concept, between these two concepts. So should be very interesting. Let me go to the next slide. So to start, we need to consider big picture what we achieved and how we deal with spaces and operations on them. So let's recall that for what we had. We had natural numbers. We also used 0. We had like considered numbers, and we had considered addition operation, right? So this was our building block. Then what we made, we took this space, just literally copied it, put close to it, and we considered, in addition to this space, we started to consider another space that encloses these two. This another space is formed by multiplication operation and some rules with multiplication, and these two spaces, left and right, with natural numbers, we say that these are standard, all standard numbers with addition operation, and these are duals. And when they considered in isolation from each other, they just exactly the same. They totally is isomorphic. There is no difference between them. But we synthesized them in some strange way, right? So one space become fractions, another space become integers. And this gave us a new concept called fractions. So basically multiplication operation allowed us to consider things like n multiplied by m, or in standard notation, n divided by m. So multiplication here is just one single multiplication operation. What we want to do, or we want to start thinking about, is to do the same trick with multiplication. So we take this one, this space, and we want to copy it. And we want to build another space around it. That new space should make these previous two, this one and this one, these previous two spaces, dual of each other. So we want to introduce dual multiplication and multiplication. And by analogy, we want to have some new operation. I will denote it with a triangle, that we form a new type of objects. So here we got fractions, and here we will got another type of objects. And this is the topic of today's video. But to simplify this, I will shrink it a little bit. So instead of having these like 1, 2, 3, 4, 5, 6, 7 spaces, I will simplify it first and I will consider only 2 spaces. They will be natural numbers, just copies of each other, with 1, 2, 3, n, 1, 2, 3, etc. n. But here I want to get multiplication operation, and here I want to get its, let's say here is standard, and here I want to have a dual multiplication operation. And I will try to find how to combine these two isomorphic spaces with a new operation called triangle operation. I could just use any other notation, just triangle is easy enough. So that's our first task today. So we want to consider, or we want to introduce standard multiplication dual, and we want to understand what is this triangle operation. So let's see, for example, if we multiply by 2 by 3, in a standard sense, we are getting 6. When we multiply 2 by 3, how can we figure out what is this, what's the number? And I suggest we will look exactly what we did for additions and just mimic it on multiplication. So on addition, the main trick that we did was the relations between part and wholes. So we know that 2 plus 2 plus 2 is equal 6, but we know if we add 6, sorry, if we add 6 3 times, we get back to 2. And we will use this principle in our case. So let's see how it looks from perspective of multiplication. 2 multiplied by 2 multiplied by 2 equal 8, but we want 8 multiplied by 8 multiplied by 8 equal 2. And this will be our basis. From this we will infer what this value is here. So let's unpack a little bit. So here we can see that this looks like this is 2 to the power 3. And here we see that this is 8 to the power 1/3. Let's unpack a little bit more. Let's give some logic to this, how this can be seen from other perspective. That's 2 to the power 1, 2 to the power 1, 2 to the power 1, right? And this is equal to 2 to the power 1 plus 1 plus 1. Here on the bottom we can write that 8 is 2 to the power, I don't need 2, sorry, I need 8 to the power 1 multiplied by 8 to the power 1 multiplied by 8 to the power 1. This is equal 8 to the power 1. Here we will use dual addition operation. And then in this case we will get 1/3 as a power for 8. Okay, looks good. So let's recall another relation for addition operation and dual addition operation. It is that if we multiply 2 plus 3, when we multiply it on 2 plus 3, what we get as a result? We get 2 multiplied by 3, and this is 6. Let's see how this expression looks in terms of multiplication. So what we have is, I want to use 2 and 4, for example. 2 multiplied by 4. We use this triangle operation that is equivalent to this multiplication operation in case of plus and dual plus. We have a special triangle operation here. 2 multiplied by 4. And we want this to be 2 triangle 4. We don't know yet how to compute this, but we want this to work, this equation. And here on the left, in terms of addition, we could say that this is 5, and this would be 6 over 5, if we compute it due to dual addition operation. 6 over 5. So we would have that 5 multiplied by 6 over 5 is equal to 6, and we are happy. So we want to have the same here. Let's try to figure out what is this. This is 2 to the power 1 multiplied by 2 to the power 2. Okay? This one is 2 to the power 1 multiplied by 2 to the power 2. Let's use this rule similar to this. Here, in our case, this is equal to 1 plus 2. This is equal to 1 dual plus 2. So this is equal 2 to the power 3. And this one is equal to 2 to the power, let's say, let's just quickly compute 1 over 1 plus 2 over 1. We need common numerator, so it will be 2 over 2 plus 2 over 1. It's 2 over 3. Okay, so result is 2 over 3. Two to the power 2 over 3. Okay, and here we have 2 to the power 1 triangle, 2 to the power 2. So looking at these, we want this to be multiplied with a triangle. So we want these both to be equal. 2 to the power 2 third. So the immediate idea here is that we want this triangle to multiply powers. So triangle will be multiplying powers of these two. And then here we get 3 multiplied by 2 third, and this is equal to the power 2 equal 4. So, and such we will define triangle operation. If we have 2 to the power n, and I have a triangle operation 2 to the power m, I define it by definition. This is 2 to the power n multiplied by m. Okay. So that's dual multiplication operation. It is defined as we see 2 to the power n multiplied it to 2 to the power m will be 2 to the power n plus m. And then dual operation will be working like this. Okay. Let's move to the next page. Now we want to establish connection with irrationality. If you remember that when we add 1 plus 1 equal 2, when we added 1 plus 1 with a dual addition operation, we were getting fraction, right? So this dual operation led us to fraction, to the notion of fraction. What is special about this fraction is that 1 plus 1 multiplied by 1 plus 1 would be equal to 2 multiplied by 1 half, and this is 1. So the fraction it plays with this original number and with this multiplication operation. It produces 1. So let's see how it looks in terms of multiplication. When we multiply, we cannot use 1 because that's not a, that's looks more like identity for multiplication instead of unit, instead of discrete. We will use 2 and we will come back to this question. So when we multiply 2 by 2, we get 4, but when we multiply 2 by 2 in dual multiplication operation, we will get 2 to the power 1 plus 1. It's 1/2 in the power, so it's square root of 2. What we get here for multiplication is 2 multiplied by 2, triangle 2 multiplied by 2, it's equal to 4 triangle square root of 2, and this is equal to, we can just deduce what is this. It should be 1, but let's see. 2 by 2 is 4. Let's see how we can compute it. Base 2, if we use base 2, 1 second. This is 2 to the power 2, 2 to the power 1/2. So this is 2 to the power 2 multiplied by 1/2. And this is 2 to the power 1, which is 2. So this is equal to 2, but 2 is our discrete unit for multiplication. So this is equivalent to this one. So what we see here is that square root of 2 with respect to triangle is a fraction of 4. Is a fraction built out of 4. So same way, so if 1/2 is a fraction in a plus sense, then square root of 2 is same fraction in multiplication sense, right? Or if I be more precise, here use multiplication and here use triangle. So these are two similar things, but one is for pair plus multiply, and this is for pair, multiply, and triangle. Okay, that's new way to think about irrational numbers, and now let's move on to duality principle. We remember that in some sense when we talked about natural numbers and dual natural numbers, we had this mapping of duality between them, and the mapping worked like this. We took n and we mapped it to n. In the standard notation, we took n over 1 and mapped it to 1 over n. And we saw a principle that we can perform operations in one space and then do a dual mapping, or we can first do a dual mapping and then perform dual operation. So basically writing it in terms of numbers, we could write that 2 plus 3, and we take dual. We are saying that it's the same as dual of 2, dual plus dual of 3. So here, if we first compute what is inside parentheses, we get 5, and we take dual, it's same as 1/5. And here, in this case, we take 1/2 plus 1/3 equal 1/5, which is the same. So that's dual mapping for two spaces that are based on addition. Let's see how this looks in terms of multiplication operation. So dual number for addition is such a number that n over 1 multiplied by 1 over n is equal to 1. In our case, two numbers n and m are dual when n triangle m equal 1, in our case 2. Let's do it. So in this case, n and m are dual, or inverse of each other. So what we can now check, if we take 2, multiply, let me write it here. If we take 2, I use base 2 compatible numbers for simplicity, and why I'm using base 2 will be clear later. And if I take dual of this, I will denote it like this. This is dual in the sense of triangle. So if we can, same way we can bring this duality inside parentheses and say that we want dual 2, dual multiply dual 4. From the other side, this is equal to 8 dual. How to compute dual? We need to solve this equation, right? Where n equal 8. I solve it this way. I write that 8 is 2 to the power 3, and I need to take dual, and this dual will be equal to, like this, root of 3rd degree from 2. On this side, let's see, dual of 2 is 2, dual multiply 4 is 2 square, we want dual. This is equal to 2 to the power 1 multiplied to 2 to the power 1/2. This is equal to 2, 1 plus 1/2. This is equal to the power 1/3, same as from the left side. So this principle holds. In general, we can write that n, m dual is equal dual m, dual multiplied dual m. Duality here in sense of triangle operation and with base 2. Okay, same way we can just check that the other way around also works. So if we have like operation like this, we will get that it's the same as this one. Okay, move on. Let's move on. Now let's just reiterate this again, that irrational numbers are fractions, but fractions in triangle sense, not in sense of multiplication. So we have, in the past we had natural numbers with plus operation, we had natural numbers with dual plus operation, we had multiplication, and we form fractions here of the type n multiplied by m or equivalent notation. So now what we got? We got natural numbers with multiplication, we got natural numbers with dual multiplication, and we got this operation, and objects here inside will look like an m, but here on the left consider hat. Let me write here hat in triangle sense. They just not ideal notation. Maybe I can just make it like a fat hat. These are not fractions, yes, these are natural numbers. Okay, so what is 1 over m equivalent? Here on the right side, 1 over m will be same as mth root of 2 if we consider base 2. Base 2 again. So irrationals here is the same as fractions here. Okay, let's move on. Let's look at why we choose base 2. We could choose base 4, base 16, or any other numbers. Let's compute. So let's see, 2 multiplied by 4 equal 2 to the power 1 if we consider base 2, b2 first. We want to consider these equations base different numbers, and we'll see that it doesn't matter what's the base, the answer will be the same. 2 to the power 2 equal 2, 1 plus 2 equal 8. Okay, let's see, 2 dual multiplication of 4 is 2 dual 2 to the power 2 equal 2 to the power 1 dual plus 2 equal dual, so we can compute this like 1 over 1 plus 2 over 1 is the same as 2 over 2 is the same as 2 over 3. 2 to the power 2 over 3 is the same as cubic root of 4. Okay, let's consider base 16. Two multiplied by 4 in base 16 will be 16 to the power 1/4 multiplied by 4 to the power 1/2. This equal not 4, 16. This equals 16 1/4 plus 1/2. This is equal to, let's see, 16 to the power 3/4, and this is 8. Okay, same 8 as we had. Let's consider this one. Will be the same, but multiplication in dual sense. Plus 1/2. This is equal 16 to the power 1/6. And this is the same as 2 to the power 4 over 6, same as 2 to the power 2. And this is the same as cubic root of 4. So we see that independent of base, multiplication and dual multiplication give us the same result. But let's take a look at something else. So if we consider base 2, this operation, it's equal to 2 to the power 1, 2 to the power 2, it's equal to 2 to the power 1 multiplied by 2, it's equal to 4, right? Base 16, this is equal to 16 to the power 1/4, 16 to the power 1/2. This is equal, let's multiply these two. 16 1/8. And this is equal square root of 2. This is strange, right? From one side. From the other side, I think this is not strange, and this is the reincarnation of the fact that, let's say if we have square and we measure it in inches, let's say it's 3 inches here and 3 inches here, its square will be 9 inches squared. If we measure it in centimeters, there may be like 5 centimeters or something like that, or 50 millimeters, okay? And here is 50 millimeters. Then its square will be 2500 millimeters squared. So kind of a different number. And I think this is the reincarnation of this principle, that if we base on this unit, we take 2 as a measurement, we get 4 an answer. If we take 16 as a 1, like discrete element, then we get answer square root of 2. That's my interpretation for this effect. Let's move on. So far I used base 2 for like numbers of some power of 2 in examples. So let's write what will it be for any if I just multiply a by b. What I need to do, I need to represent it as a power of some base. I can take 2, 3 or whatever. I just, for simplicity, will choose e, because mathematics like e is some special number. So it will be ln a plus ln b. A multiplied by b, dual multiplication, will be equal to ln a plus ln b. A triangle b will be equal e to the power ln a multiplied by ln b. And let's just multiply these numbers so that a multiplied b triangle a multiplied b equal. If we substitute e to the power ln a plus ln b multiplied by ln a plus ln b, and we know from our multiplication and addition and dual addition spaces that this is equal to ln a multiplied by ln b. So we see that this one and this one coincide, so it kind of, this new algebra that we built today is compatible with the previous one, with additions and multiplications. Yeah, I think this is all that I wanted to show. So in this video we introduced multiplication operation, its dual and triangle operations in complete analogy with plus, dual, plus and multiplication operation. Here I want to notice, if we try to continue the sequence of operations like plus, multiply, what is coming next, in a standard way, then this like square operation, in a standard way it's defined more like 2 to the power 2 to the power 2, or maybe it's the opposite, the other way around, like 3 to the power 3, so something like that. So this is not commutative. I think it doesn't play nicely with some other aspects of algebra. In my case, I define triangle operation in a very convenient way. I think it makes sense to go this way instead of just this square operation. So we introduced duality principles. So for just standard multiplication operation, duality is achieved through this relation, and in my case duality is achieved like this, with the notion of triangle operation, and this will be cubic root of 2, and this is equal to 2 because 2 is a unit for multiplication. So this is the duality principle, and we showed similarity of fractions with like complexes built. So just let me explain. Fraction is something built around multiplication operation, and in our case we built around triangle operation, and on this side we have irrational numbers, and here we can have just natural numbers. So we showed complete equivalence or similarity between these two. Okay, that's enough of this video. We have not covered a lot of things, like we didn't cover distributive law, we didn't cover identity elements. We didn't cover like things. You remember in the past we were saying that 0 multiplied by 0 is equal 1. In case of triangles, that will be looking more like 0 to the power 0 or something like that, I guess. It should be equal to somewhere, to something. So there are a lot of things to consider here. So also want to just to mention that plus, multiply, triangle looks like this is a more complete set of operations to handle numbers, fractions, like rational numbers and irrational numbers in a more consistent way. So there are a lot of things we can do starting from this. So please hit the subscribe button, hit the like button, and see you next time.